Okay, 10.6, exponential growth and decay. Students will be able to use logarithms to solve problems involving exponential growth and decay. Okay, exponential growth. This is simply when an exponential model grows or gets bigger. And exponential decay is when an exponential model gets smaller. So the percent of decrease, R, is also referred to as the rate of decay. Okay. Now, we're going to have a few different formulas here. There's going to be two that are exponential growth and two that are exponential decay. Here's the first exponential decay one. This is typically used for value, so for like a car's worth or you know, a stock or all different types of things that have to do with money. And it can also be used for some scientific things, but typically this is not the one that we use for scientific things. But it can be used for something like, you know, if your body is burning off some type of compound, you can use this type of formula. So let's take a look at the very next problem we're going to do. Hey, look at this. A cup of coffee contains 130 milligrams of caffeine. If caffeine is eliminated from the body at a rate of 11% hour, how long will it take for half of this caffeine to be eliminated from the body? Okay, so this is we can use this type of problem, or that last equation with this type of problem. So our equation we said was y equals a 1 minus r to the t power, where a is our starting amount and y is our ending amount. So what did we start with? Well, we started with 130 milligrams, and we want to get to half of that, so that's 65. And we have 1 minus, well, we're decaying at a rate of 11%, so we do 1 minus 0.11, and we're trying to solve for t. Okay, well, 1 minus 0.11 is 0.89, and if I was to divide both sides by 130, 65 divided by 130 is just 1/2, so we get 1/2 equals 0.89 to the t power. All right, well, so this is really just a logarithm problem. We're just going to solve for t, so right now we have a variable in the exponent, so we just need to move it into log form. So that's like this, log base 0.89 of 0.5, because this is really just 0.5, equals t. So we can just plug this into our calculators like so, if you have that kind of calculator. Otherwise, you're going to have to write it as log 0.5 over log 0.89. And you get t equals about 5.948 or so. Yeah, 8 or so. So about 5.948, or we could just say, hey, it's going to take about 6 hours to burn off half of that caffeine. Okay, so there you go. There's the first type of problem with the first type of formula. Next one says, example number 2, the half-life of a radioactive substance is the time it takes for half of the atoms of the substance to become disintegrated. This uses the formula y equals AE negative KT. Okay, so now, look, we're talking about atoms, we're talking about things disintegrating. This is more science. We're going to use this type of formula. All life on Earth contains a radioactive element, carbon-14, which decays continuously at a fixed rate. The half-life of carbon-14 is 5,760 years. That is, every 5,660 years, half of a mass of carbon-14 decays away. So what is the value of K for carbon-14? Well, let's try and look at this equation. We got y equals AE to the negative KT. Okay, well, what's our y? Well, it doesn't really, let's think about this. If we started with A, we're saying it's going to get to half of A. So this would just be 1/2 A equals A, E, negative K. How many years does it take to get 1/2 A? We already know. It's 5,760. All right, well, let's think about this now. We could divide both sides by A, and the A should just cancel out completely, and we just get that 1/2 equals E to the negative 5,760K. Well, we can rewrite this as a log. And it's, in fact, since we have an e, we can rewrite it as a natural log. So I told you guys there's a few different ways to think about it. We could think about it as taking the natural log of both sides, which leaves us with the natural log of 1/2 equals, and we said when we have a natural log of e, it's just whatever the exponent is, so that's just negative 5760k. Divide both sides by negative 5760, and this is your k value. Plug that into your calculator. So the natural log of 1/2 divided by negative 5760 is, my answer comes back in scientific notation in my calculator, so I'm going to have to throw in a few zeros there, but it's 0.3 zeros and then a 1 and a 2. So that is my k value, 0.00012. Alright, so on this next part of the question, it says an archaeologist examining the bones of a woman estimates that they contain only 33% as much carbon-14 as they would have contained when the person was alive. How long ago did the person live? So this is a relatively accurate way that archaeologists actually do date things. Not a perfect system, but it can give them some pretty good numbers to work with. Since we know what the carbon-14 was of a person that lived so long ago, we can also know, about how long ago they lived. So let's think about this. We want 33%. We want to end with 33% of our original, and our original is A. So we would say that's got to equal A times E to the negative k value, which is 0.0012, and then times t, which is the time that we're going to try and solve for here. So we could divide by A, the a's cancel out again, and we're left with 0.33 equals e to the negative 0.00012 t. Once again, we're going to need to solve for a variable, so we can do this by taking the natural log of both sides. And so we have the natural log of it's a weird 3, 0.33 equals, and then the ln e just cancels out, and we're left with just what the variable, just what the exponent is, which is negative 0.0012 t. And so now we need to divide both sides by negative 0.00012, and this divided by negative 0.00012. These guys cancel, and so your time is going to be whatever this is. So go ahead and plug that in your calculator. And when I plug that in my calculator, I get that the time is approximately 9,238.9 years ago. So roughly 9,000 years ago is when this person lived. So that's the idea of how that would work. Okay, here we also have another formula. This is exponential growth, and this can be quantified with the formula y equals a times 1 plus r to the t. This is the same as the first formula I gave you. The only difference is now this is a plus r because we're growing instead of a negative r. And here you're going to see another equation down here in just a little bit. Notice this is another exponential growth, and this is AE KT. So the only difference between this and the other formula is that this is a positive KT instead of negative KT. So really they're the same formulas. One's got a plus R instead of a negative R, and one's got a positive K instead of a negative K. I'll zoom in here so you can see what I'm talking about. See, positive K, and the last one had a negative K. Okay, so example number 3. In 1910, the population of a city was about 120,000. Since then, the population has increased by exactly 1.5% per year. If the population continues to grow at this rate, what will be the population in 2015? Okay, well, we know that the initial population is 120,000. And A stands for the initial here. Our rate of growth is exactly 1.5. So we would say 1 plus 0.015. That's how you would write percentage as a decimal, 0.015. And how many years will it be from 1910 to 2015? Will it be 105 years? Okay. Well, we just have to plug all this into our calculator to figure out what we get now. We got it all set up. We can simplify a couple things, though. So we know that it's 120,000 times 1.015 to the 105 power. And yeah, from here, this is really just plug that in your calculator, see what it gets back. So I'd go ahead and do that. 120,000 times this to this power. And only 1.015 is to the power of 105. Okay, when I plug all that in my calculator, I get 572,948.63. Well, obviously we're talking about population here. So we're going to say something like the population should be, and we can just kind of round it, should be about 572 or maybe 73,000. Right? That's really close to 573,000. So that should be what our population of the city is after 105 years. Okay, now that's one way to calculate population. We could also calculate population using this exponential growth equation. So usually this is going to be a little bit more scientific, or you'll see like scientists doing this. So here it says, as of 2000, China was the world's most populous country, with an estimated population of 1.26 billion people. The second most populous country was India, with 1.01 billion. The populations of India and China can be modeled by, here we have one equation, I to the t, and c to t. According to these models, when will India surpass China's population? So we really want to know, when will India, the function that represents India, be greater than the function that represents China? That's what we were really interested in. So let's just plug in what we know. Well, we know that I of t is 0.01 e to the 0.015 t. And China is 1.26 e to the 0.009 t. And so you can see by looking at the function above, k is kind of like our growth rate, or something to do with our rate. And this one's a little bit bigger in India than it is in China. So even though China has more, India's growth rate is higher. Okay, so how could we solve this guy? Okay, well what we can do is we could take the natural log of both sides. So I'm just going to slap a little natural log in front. And we could split this up, because this is 1.01 times e. So I could write this as the natural log of 1.01 plus the natural log of e with a power of 0.015 t. So I could bring that out here as a coefficient. So I've just expanded this expression as two logs and moved the exponent out in front. And I can do the same thing over here. So this is the natural log of 1.26 plus the natural log of e, and 0.009 t becomes the coefficient now instead of the power. Okay, let's get all the t's on one side, and let's get all of the numbers on another. First of all, we should already know that natural log e is just 1. Natural log e is just 1, so we don't even really need those anymore, because 1 times anything is itself. So let's subtract 0.009 t from both sides. And let's add, or actually subtract ln 1.01, natural log of 1.01 from both sides. These guys would cancel here, and these guys would cancel here, so we would have 0.15 minus 0.009 is 0.006 t. And over here we would just have ln 1.26 minus ln 1.01. Now we could combine these, but we don't really need to because we're going to be plugging this into our calculator eventually anyway, so I'm just going to leave them like this. And my last step is to divide both sides by 0.006, and you get that t has to be greater than the natural log of 1.26 minus the natural log of 1.01 all over 0.006. Alright, so that's your answer, but to get your final answer, you're going to have to plug that into your calculator. And so when I do that, I get that t has to be greater than 38.8602. Okay, now let's go back to the original question. What did that mean? It was 38.8 years after what year? After 2000. So we could say that India will surpass China in population in about, well, what year would that be? Well, 38.8 is really close to 39, and we're starting at the year 2000. So in about the year 2039. So there we go. Math can make predictions like that. All right. Hopefully that made sense. If you guys had questions, make sure you bring them to class on Monday before the test.